Yes. Welcome everyone to today's instrumentation colloquium, the Interdisciplinary Instrumentation Colloquium here at LBL. And we are really happy to see so many people joining us in person and online. Today's speaker is Hans Bechtel. He's a staff scientist at the ALS, and he's really shaping the IR aspects at ALS for a long time now. So he joined ALS in 2007. And before that, he already worked on vibration spectroscopy during his postdoc time at MIT. And before that, he was already in California and Stanford doing his PhD there, also working on vibrational spectroscopy, as far as I understand it. And yeah, he has authored a lot of publications with many different aspects of IR spectroscopy and synchrotron applications of it. And we are really excited to hear from him a little bit about the history of the IR efforts at ALS, the capabilities, the current capabilities, and also, of course, about the future plans connected to the ALSU upgrade and what we can expect maybe to do in the infrared spectrum at ALS in the future. So let me welcome Hans, and I'm looking forward to this talk.
All right. Thanks, Tim. Thank you for inviting me. And thank you, everyone, for coming to spend your lunch to hear about IR at the ALS. So I have Grover here to help a little bit with far and near. Hopefully you'll figure this out throughout the rest of the talk. But let's jump into it. So as many of you already know, the Advanced Light Source is one of the many national user facilities here at LBL. It's the premier soft X-ray light source in the nation. And really our mission is to advance science for the benefit of society, for providing our world-class synchrotron light source capabilities and expertise to a broad scientific community. And so the ALS started operation in 1993. It has, the past 30 plus years, it's been producing lots of great, fantastic science. We have about 300 staff that support a little over 2,000 users a year. And we have lots of different publications coming out. One of the key things is that we have now around 43 different beamlines. If you look at our clock, these are all the different beamlines we have at the ALS. And maybe, for those of you who aren't familiar, right, the ALS is a particle accelerator. So we start with electrons in this linear accelerator, excite them to like 55 millielectron volts. Then they go into this booster ring where they get accelerated even more to the full 1.9 gigaelectron volts of the storage ring. And then they get injected into the storage ring. As electrons move around, they go in this nice circle. It's not a real circle, it's actually segments. But they go through different sources, and we have them listed here. There's insertion devices, there's dipole bin magnets, and then there's super bins. So the insertion devices are really what makes the ALS what's called a third generation light source. They're basically, instead of having, we'll start with the bin magnet. So bin magnet's a simple dipole magnet. That's what causes the electrons to move in their bin path. And then in the straight sections, we'll have these insertion devices. And these are periodically poled magnets that cause the electrons to slalom. And the reason we do that is then you can get higher brightness and more monochromatic X-rays coming out. And then the super bins are specifically meant to increase our energy, so you have hard X-rays can come out of those. So those are sort of the different sources. But as you sort of look through this list, what you see is really a lot of X-ray beamlines. And that is, of course, what the ALS was built for. It's what synchrotrons are built for around the world. But it turns out they also make infrared light, okay? And so if you look at one of these dipole bin magnets and look at the light that's generated from them, you'll see it's very broadband, ranging, we like to think of in terms of photon energy and EV at the ALS. And so it goes from, thousands of EV down to very, very milli EV. And so that milli EV region is where infrared light is. And so this region I've highlighted in pinkish red, you can see is the infrared light. And I guess, so you're sitting there, it's like, okay, so what? My toaster oven makes infrared light, my lights make infrared light. Uh, and probably some of you have been in a chemistry department where you've used instrument, an FTIR instrument that also makes infrared light. And so it's not just the fact that it makes the light. The real point here is this right-hand magenta curve is the brightness. And it's that this brightness happens to be about 1,000 times brighter than a conventional black body source. And so what that means is we can focus that light into a very small spot. And this simple graph is showing how we're doing that. So if you take this black curve, this is a typical thermal source you'd find in a conventional FTIR instrument called a glow bar. And if you try to focus it through a small aperture and you close that aperture down, you'll see that basically the flux that goes through that aperture gets smaller and smaller. And so your signal to noise gets smaller and smaller. You do that with synchrotron light, and it goes through that aperture until you start closing to what's called the diffraction limit. And then that's the smallest you can focus the light in the far field, and that's when you start to close it down. So at the ALS, what we then use that for is to do diffraction limited microspectroscopy, so infrared microspectroscopy. And we've been doing that for about 30 years, and I'm going to give you some examples about that. More recently, it's now been a little over a decade, we've also been doing what we now call nanospectroscopy with infrared light. And this involves focusing light onto an AFM tip and using that tip as an antenna. And that antenna basically focuses that light down to the tip radius. And so now we can get spectral resolution on the order of the tip radius. And so with the AFM tips we typically use, that's about 25 nanometers. So those are the two main things we do with ALS. And I will go into more details on how those work in the next. But maybe I'll step a little bit further back and say, okay, IR spectroscopy, why do we care? So IR spectroscopy, it's used to measure low energy excitations, and in particular, molecular vibrations is the key thing that it's often used for. But it's also, we can measure band gaps, we can measure other aspects of quantum materials as well, excitons, polarons. And so it really covers a wide range of materials that we can measure. And so for that reason, it's almost everything has an infrared spectrum of some sort. There's a few things that don't. But I like to say we measure everything from deep Earth to deep space and everything in between, right? And so these are just some examples. We've measured some, rocks from volcanoes. We've measured diamonds that are extracted from the center of the Earth, looking at inclusions in those diamonds. And particularly, we've determined various levels of forms of ice that have been compressed in that diamond. We've looked at 2D materials. Some of the first measurements on graphene were actually at the infrared beamlines at the ALS. We occasionally get mummy bones to look at. And one of my favorite things, of course, is looking at extraterrestrial materials. And so we've looked at cometary dust. We've looked at dust from out of our solar system. More recently, we've been looking at asteroids. And so both from Bennu and OSIRIS-REx, NASA's program, and Ryugu from the Japanese mission as well. The other good thing about IR is it's not ionizing. And so that means you can shine it onto living things and not cause damage. And so we do a lot of our work actually on biological materials as well, and including living cells. So we can shine light, infrared light, measure chemistry of a living cell for hours, even days on time without causing any damage to it. All right. And then just to show sort of how our shifts get allocated, I mean, these are part of our general user program. You apply for beam time and you get allocated based on a peer-reviewed score. And you can just see from this graph that we do a little bit of everything. And that's consistent with what we do. So the people, we now have 4 people on staff at the infrared beamlines. So there's me, and then Stephanie and Diana are the other beamline scientists. And then John recently joined. He's doing a lot of instrumentation to us as well, which we'll talk a little bit later. We have 3 infrared beamlines. And so the first beamline that was built was 1.4, and that was for about 10 or 15, almost 15 years, I guess. And then we built 5.4 and then 2.4. And now we have 8 different instations that we're currently supporting. So we have our original Nick plan IR microscope that was the first instrument we had at the Beamlines, still going strong and still our workhorse for infrared microspectroscopy. We have a new photothermal Mirage instrument, which is based on, which now gives better spatial resolution. It's diffraction limited and visible. And so this offers some unique things to look at. We have a NeoSpec near field instrument. We have a focal plane array system. So this array now has a detector that you can measure 16,000 spectra at one time. We have a second, this is actually our original near field instrument, Bruker and Nova, based on Bruker and Nova. This is one that I helped put together. And then we have some more far IR microscopes. We also have a high spectral resolution infrared microscope, or it's not a microscope, just mainly for gas phase that can do ultra high spectral resolution. And then we also have a Raman microscope that you can do for complementary measurements. All right, so that's what we do. And so the question is, what does an infrared beamline look like? And so I'm going to start by talking about an X-ray beamline. So there's a lot of those at the ALS if you go up there. And so this is a typical one. And what you'll find, of course, you have your X-ray source. In this case, I'm showing an undulator. You typically go through an aperture, and then you'll have a mirror or two to start shaping the beam. And then you go to a monochromator, which then takes what can be broadband light into a single frequency. Then you might have another mirror, and where our newer beamlines are starting to have adjustable mirrors for adaptive optics that can really focus in tightly. And then some exit slits, and then you end up with an end station. That end station can be a number of things. It really depends on the type of measurement you're trying to do. And different detectors, different techniques. You can do diffraction, you can do photo emission, you can do a variety of crystallography, all sorts of things. But almost all the beamlines, if you look at the end station and then look back towards the shield wall, it looks like a big metal pipe going straight back, right? And that's because one, everything's enclosed in vacuum because X-rays get absorbed, and well, they get absorbed, soft X-rays in particular get absorbed by the air. And also there's a radiation risk, so that's also a shielding. So you want to keep that confined. But they look like lines because you can't use normal mirrors to reflect X-ray light. You have to really go at these grazing angles. And so even if we have a bunch of mirrors, it's still deflecting the beam only slightly. So you see these long lines. Okay. Infrared beamline looks very different. Okay. And so one of the first things, so for infrared beamlines, we do almost always use a dipole source. It's broadband radiation. And usually the mirror, the first mirror is integrated very closely with the accelerator. And so I'll show you an example next of where it's intimately next to the accelerator. The next thing we do is we'll have a focusing mirror or maybe a pair of mirrors that will focus the light through a diamond window. And that we use diamond because it's the material that basically allows as much light through spanning the whole infrared region. And it serves a critical thing, it serves as or basically separates the ultra high vacuum of the storage ring from rough vacuum and air for the rest of the beamline. So we're basically focusing through this small diamond window, and then we take our light, we collimate it. That can be with a couple mirrors. And then we have a few more mirrors that are steering it into our end station. And so the other thing you see here is I've listed, instead of having a monochromator, we have an interferometer. And so in this case, and I'll show you some more examples too, we are using the broadband light and interferometry to do our spectroscopy, not using dispersive gratings or prisms. All right, so this is what it looks like in sort of more real terms. And so one thing to note, so the natural angle of light coming out of a synchrotron is dependent on the wavelength and the bending magnet radius. So that's, goes as the third power of the wavelength. And so you go to long wavelengths like infrared light, that means you need larger and larger opening angles to collect all the light that's coming out. And so if you use the traditional X-ray ports, they're located much farther downstream from your source. And so the chamber of the accelerator actually starts to block the light that's coming out. And so our first beamline actually uses that. And so our light is limited by the actual accelerator chamber. So for our new beamlines, what we did is there's a port that's immediately after the third bend magnet in the sector, and we can take light out of that, and so we send the light up out of plane. And so you can see how we have this mirror. It's aggressively water cooled, and it's put right into the accelerator chamber. And so you can see this little hole here is where the electrons are going. So it's very close to the electrons. And using these mirrors, we can get twice as much light coming out. That's what we do. The other thing, infrared light can use normal mirrors to reflect any of which direction we need to go. And so beamlines, IR beamlines actually don't look like lines. They're a bunch of going multiple different directions. And so this is the case of beamline 2.4, where it actually goes up, out. We have some focusing mirrors, and then it actually turns and goes upstream and then out the shield wall. 5.4 is actually even more convoluted. It actually goes out, down, and then it runs underneath a tunnel underneath the storage ring, and then pops back up in the center, where we have a nice building up there we call the penthouse. It has a good view of a porch and everything. But it's a place where none of the X-ray beam lines are fighting us for space. So we have a nice little space up there. And so if you go back to the clock, normally if you go up to the ALS, it's easy to navigate around. You go clockwise and the numbers will increase based on the port, and you can walk around. But infrared beam lines can be tricky to find because, well, 2.4 I said went backwards. So 2.4 comes, before 2.1 and 2.0. And then if you can keep walking around forever and never find 5.4 because it's in the center of the ring. And so even some staff who have been around a while have trouble finding 5.4 sometimes. Okay. All right, so now to instrumentation of microscopy. So I said we make use of interferometry. And so this is basically a Michelson interferometer. It's the same sort of instrument you'll find in any chemistry department doing FTIR. And basically the key is there's a beam splitter, there's a moving mirror, there's a fixed mirror, and then they get combined after going up through your sample onto a detector. And so if you look at that detector response as you move that mirror, you get what's called an interferogram. And that's because different parts are interfering, different wavelengths are interfering at different points. But at the zero path difference, the path where the reference and the moving mirror have the same exact length, everything constructively interferes at the same point. And so you get this really big signal. But then the wings are actually what are the interesting parts. And so it looks like it's zero, but if you zoom in, I've zoomed in 300 times here on this inset, you actually see some more wiggles. And then that's actually where you get the spectrum, the interesting vibrational features. And then the longer you scan that mirror, the more spectral resolution you get for your sample. All right, and then once you've acquired the raw data, then you do a Fourier transform, and that gives you your spectrum. And this is showing the typical spectrum of our instruments at the ALS. Very broad band covering, in this case, the mid IR into the near IR. And I'd say the low end is limited by the detector in this case. So after this interferometer, I show sort of a schematic of a microscope. Here I'm showing a case where we're measuring in reflection mode, where you reflect off your sample and then go back to your detector. We also can measure in transmission mode, and that's actually, in many aspects, the preferred way of doing it. That makes analysis easier on the end. And then a lot of the sort of instrumentation side is then how do you put your sample in that focal plane? And so there's a lot of flexibility. We have different objectives, so we can have different focal lengths to put in there. So 8 millimeters, 15 millimeters. And so that gives room to put, diamond anvil cells if you want to look at things at super high pressure. We can put in cryostats if you want to look at things that are cold or heated. And then the other thing we do a lot of is look at microfluidic cells. Because one of the problems with IR microscopy is that we're trying for a lot of our experiments, we want to look at biology, and you want to look at biology that's living. And so in order for biology to live, you have to have water. And the problem with water is that it absorbs IR very strongly, right? And so then if you have too much water, you don't get an IR spectrum. But if you don't have enough water, then you don't have life. And so there's this Goldilocks problem to fight just right. And so Huiying Holman's group here at the lab in NBIB, she runs this program called Berkeley Synchrotron Infrared Structural Biology Imaging Program. She's developed a lot of resources developing microfluidics to really control the amount of water. And the right amount of water is like 5 to 10 microns. So that's sort of where that's the sweet spot of thickness. And so that's enough to hydrate your cells, but it's enough to penetrate some infrared light through. And so one example of this, so this goes back to actually 2010 when there was this big Gulf oil spill where researchers from the lab actually were sampling the oil spill. They found this plume of oil about a mile below the surface and sampled that, brought it back to the lab. And we were able to look at that at our instrument and actually watch some native microbes consume the oil and degrade that naturally, right? So these are microbes that were already around. And, because the Gulf is constantly seeping some oil. And so they've developed ways to consume and biodegrade that oil and use it as energy. And so so these are some spectra. So you can easily identify where the oil droplets are. And then we get spectra that look like this that have strong protein characteristics, and that shows us where the microbes are. And then what we can do is we can do maps. So we can collect spectra and raster scan and build up these hyperspectral images and identify, spectrally where these images. And so we get proteins, we get carbohydrates, and those are showing us where the microbes are. Alkane, of course, showing us where the oil was. And then we can monitor these over time and look at how the chemistry is changing. And I like to point out, so we have two different communities of microbes here consuming oil. And over time, one is doing an oxidation process where they're using oxygen and making products with oxygen. And this other one, this lower one, is actually using the sulfur chemistry and degrading the oil using sulfur products. So that's interesting to see, right? And so we can do this with biology. We can do this with other things. And the question though is, what if I want to look at one microbe, not a community of microbes? Or what if I want to look at some electrochemical cell that has heterogeneity, that's sub-micron, right? And so that's where I say IR has this wavelength problem, right? So it's your resolution from a far field measurement is determined by diffraction. And so that's determined by the wavelength and then the numerical aperture of your objective. And so for the objectives, standard objectives we have, the NA is on the order of 0.6, 0.7. And so really our resolution at the beamline is limited to about the wavelength of light. So in the mid-infrared, that's 2 to 10 microns approximately. To get smaller than that, you have to go towards the near field. And one way of doing that is to get an aperture and scan it really close to your sample. So that's, when I say really close, that means less than the wavelength of light. So again, that'd be less than a micron scanning. And you can do that, and people have had a lot of success in getting near-field spectra or near-field spectroscopy that way in imaging. The problem is that your signal scales to the fourth power of your aperture size, and then also your wavelength. And so if you're looking at already long wavelengths, and then you're trying to shrink your aperture even to nanometer size, then your signal to noise gets very bad very fast the smaller you go. So another way of doing this is not this aperture-based technique, we use an apertureless way. And so one of this newly, well, now almost 20 years old, developed technique is called SNOM. So this is scanning near field optical microscopy. And so it combines an AFM with an optical source to get near field images. And so again, here, we're going to take our light from the synchrotron. We're going to send it into a Michelson interferometer. What's different here, though, is that we're going to actually put our sample as one of the arms of the interferometer. So this is what would typically be the reference arm. But now we're going to put our sample in an AFM, and we're going to take a parabolic mirror. We're going to focus our synchrotron light onto that AFM, and then we're going to collect the scattered light coming back. On the other arm, we again have a moving mirror that then moves and goes to our detector. And so you'll see there's two things moving here. So we're going to be operating in tapping mode. And then we're moving our reference mirror to get spectroscopy. Okay. So just to show you that this does indeed work. So this is an example of SiO2 on silicon, have little holes of where the silicon is. And so we can do a normal topography scan, and that gives us a topography image, so a height image. So in this case, SiO2 is higher than the silicon. And then while that's scanning, we can collect the broadband light that's getting scattered off during that scan. And we can see where the SiO2 is darker than the silicon, because silicon reflects more than SiO2. This scale bar here is 100 nanometers, just so you know. And so if you do just a cut across this, we're really seeing resolution of less than 25 nanometers. Okay. Great. So, how do we actually achieve this, right? So we're shining a diffraction limited light onto a tip, and the tip is small, but we're still going to get scattered light coming off everywhere. And so the way to minimize this scattered light that we don't care about, I mentioned we have two modulation techniques. And so if we look at our interferometer and look at our detector, the light that's being hit, we have signal coming from the near field, we have signal coming from background scatter from wherever, and then we also have signal coming from a reference arm. So if we square all that, we get this messy terms, and so that's a lot on the detector. And so thing to note that is in our favor if we're tapping. And so the near field response is very nonlinear with sample distance, right? So as you get closer and closer to your sample, near field signal goes up. And so if we're oscillating our tip in this nice sine wave harmonic fashion, what we see is that the tip, as it gets closer and closer, it peaks higher. So then if you go back into your Fourier transforms, you do that, and again, you'll say, okay, well, I'll have a component that is the harmonic oscillator, but I'll also, because it's sharper than a sine wave, I'll also get higher harmonics of that. And so what if we detected these higher harmonics of the tapping frequency, then we're going to be more sensitive to near field than the background. And so by detecting that, typically we'll detect a second harmonic or third harmonic, we can get rid of some of these terms. But there's still this term left where there's the near field on the background. And this is still spatially dependent. So as we scan, we can get different background contributions. And so the way we get rid of that is actually with again, with our reference mirror. So when we take that reference mirror moving, and then we do a Fourier transform of that signal, the terms that are in this near field squared term and this near field background term, they're basically a constant in the detector. And then we only are left with this near field term times the reference. And so this shows us that, we get near field signal without background. And then we also get our signal is boosted by the reference power as well. So we can increase our signal. All right, so now we do spectroscopy. So again, this is our interferogram. And the other thing that, since our sample is part of the interferometry, it's called what's now an asymmetric Michelson interferometer. And so rather than just getting the amplitude data, we can get both amplitude and phase from that interferogram. And so you can see in this SiO2, it's an asymmetric interferogram. And then silicon, which is basically reflects almost all wavelengths equally, it looks more symmetric. And so then you can ratio those two and extract your Fourier transform. So you get your amplitude spectra, you get your phase spectra. And to first order, the amplitude spectra looks like your the real part of the dielectric constant or the index of refraction. The phase corresponds to the absorption or the imaginary part of the dielectric constant. And so for weakly absorbing things like molecules, that first approximation works pretty well. Something like a SiO2 actually has a strong phonon mode that you can almost do this Fourier transform by yourself, by head. You have to do a little bit more modeling and fitting to extract these parameters, but there's some fairly simple models to do that, and there's also some very more complex models to do that. All right, and then with this technique, we can do point spectroscopy. We just showed that. We can do line scans, and then we can also do area scans. I will say that area scans do add up quite fast in terms of the time required. That whole n squared scaling factor does add up. I mean, typically we can do a single spectrum in about, well, in a minute to 10 minutes, depending on what you're looking at. And so you can do the math to figure out how long it takes to do some of these things. But again, line scans we'll do in a couple hours. Area scans can take half the night if you want. All right, so the other piece to this is then the detector. So I already mentioned that synchrotron light is broadband, and so it goes from far infrared or terahertz all the way up to X-rays. But the challenge that we have to do this technique is the detectors. So we have lots of detectors, but for far infrared or measurements, particularly, but they tend to be bolometers because they're very sensitive. But the problem with bolometers is they're also very slow. And so if you're trying to detect a tapping frequency of your AFM tip, and we typically use AFM tips with tapping frequencies of 300 kilohertz or so. And so that means to detect a second or third harmonic, you really need to be able to have a detector bandwidth on the order of 500 kilohertz to a megahertz, ideally. And so there's different, detectors we can use. MCT is the common one that it's liquid nitrogen cooled normally. And so that's what's used often for even far field measurements. But pushing this region to the far field, or far infrared, sorry, gets more challenging. And so the one that we've been using most recently is actually, again, MCT, but instead of using liquid nitrogen, we now use liquid helium to cool it. And so by doing liquid helium, that shifts the band gap further down. So now we can get down to about 180 wave numbers. It also has the advantage of boosting sensitivity as well. So we do both of those. And the reason we're really interested in the far IR, there's a lot of neat phonon modes, neat science we can do with this. That's not accessible with current infrared lasers. And the lasers tend to stop working around 700, 600 wave numbers, whereas we can go further than that with the synchrotron source. All right, so using this nanospectroscopy technique, we can do a lot of different techniques again, or a lot of different fields. So these are just flashing a few of them. I'm going to just give one example today, which is on polaritons. So a polariton is a quasi-particle that you get from mixing, a phonon, so optical phonon, with some other electromagnetic feature of solid. So it could be a plasmon, it could be, a polariton, a phonon, it can be the magnon, all these other things. So we're going to talk about phonons. So phonons are collective oscillations in solids. And you get propagating phonon polaritons when the real part of your dielectric constant is negative. Okay. And so these have been around, people have been studying these for a long time, but with far field light, with infrared, it's actually hard to excite these unless you have some edge or defect, because there's not enough momentum to excite these phonon polariton waves. But now that we have this very sharp tip, that induces, we have a lot of momentum now that can excite these waves, and they'll propagate radially from the tip. And they'll propagate along, and then they'll decay with scattering. And so you don't really see them if you're in the center of the sample. But as you scan your tip to an edge, what can happen is the polariton can reflect off that edge and then come back. And then now you're in this situation, we're doing more interferometry, right? So you can, depending on where that location is the tip, you can get constructive or destructive interference at that tip. And so you get these nice wiggles that show you where the polaritons are. And so if we look at a common, van der Waals material, 2D material like boron nitride, there's two phonon modes that it has where the index of refraction goes negative. So there's this lower band right around 800 wave numbers. And then there's this upper band between 1400 and 1600 wave numbers. And if you scan your AFM tip near the edge and scan across, we can create this beautiful image here where we're seeing, on the lower, we have distance and then frequency on the top. And you can see these nice dispersive waves as these polaritons propagate. You can do line cut. So let's do line cuts of, position, and you see spectra, and you can see these polariton waves features. You can also do frequency cuts, and this is where you see the nice sinusoidal motion. You can fit those and then extract the polariton wavelengths from that. Great. So that was HBN, and this is an example so HBN is isotropic in plane and anisotropic out of plane. We can take another 2D material like molybdenum oxide. This is fully anisotropic. It has a number of phonon modes that we can look at. So then again, what we're going to do here is do a line scan across one edge and a line scan across the other edge. And so then we have this beautiful pattern that shows up. In this case, because this is a ribbon, we're actually creating a Fabry-Perot resonator. And so now you see these beautiful Fabry-Perot resonances as you scan across. And what you see clearly here is that if you scan one direction, you'll see the Fabry-Perot resonator response. And if you scan across the other direction, you see it in the other phonon modes. And this has to do with the anisotropy of material. We can zoom in, and with our instrument, we can go super high spectral resolution. And those are actually shown to be some of the highest Q factors for these Fabry-Perot resonators of these phonon polaritons. And so the idea ultimately is to use these to control light at the nanoscale. And so this is one step towards doing that. Okay, so everything I talked about so far has mainly been at room temperature. And so then the goal is, well, if we look at these phonon polariton modes, we could go colder, these phonon polariton modes will propagate further because there's less scattering involved. And so there's other things we'd like to look at if it's cold. So, correlated materials, you can look at phase changes going from, insulator to metal transitions. And you could look at charge ordering as a function of temperature. And so with that, though, you need a way to do instrumentation, this technique, with a variable temperature. And so that's what we've started working on now. It's a project called Cryosens. And the idea is to have variable temperature. We want to have it in UHV conditions so that when we're at the coldest condition, We're not getting water deposited on our surfaces. And it also will make it compatible with the other ALS techniques. So we can have a vacuum suitcase to bring different samples across to different techniques. And then the other big thing is, we want to make this as user-friendly as we can. And so what that means is, we typically have users coming for a week at a time. And if they want to put their sample in, you want to be able to have their sample in and be able to measure, fairly quickly. Or if, let's say, they break an AFM tip, you want them to be able to fix that AFM tip really quick. And so we're designing ways to do in situ changing of the sample and tips, not having to vent the chamber, insert a new tip, pump back down, 48 hours later, and then start over, right? So that's the goal. And so our design is actually we're building off of Alex McLeod's design, who's at the University of Minnesota. He's built several of these. We're modifying even more. So Stephanie and particularly John is working on upgrading this design to make it suitable for the ALS. And so we have this, design reviews have been completed, and we're actually starting to get material now, parts in. And so John is starting to build that up. And so the goal is to have this first start testing in the next few months. And then, late next year, we'll actually have this fully working and available for users. And so we're really excited by this new type of new science that this instrument can build. All right. So speaking of future, so many of you already know that, the ALS is undergoing a major transformation here in the next few years. It started already. And so this is the ALSU project. And basically the idea is we're taking light, where today's ALS, our electron beam looks like a pancake, and we're going to make it and look like a pencil. And what that does is it is going to increase the brightness and specifically the coherent flux for soft X-rays. So then the question then is, what happens to infrared light in this upgrade? And so fortunately, one of the high-level goals has always been to provide infrared light comparable to present-day ALS. And that's not always, for these new machines, this is not always a given that you can do that. And that's because these new machines, as you see, as we'll see, the chambers get smaller and smaller. And as I already said, we need large extraction angles to get infrared light out. And so these smaller chambers make it complicated for infrared light to come out. All right. So the ALSU scope is basically installing two new accelerators. One, we're going to have what's called an accumulator ring, and then we're also going to have a new storage ring. And so this accumulator ring has already been installed. It's going to start testing here in the next few months. And the storage ring is going to be installed, we believe, sometime starting next year, probably late 2027. So how does this pertain to IR? So I'm showing one sector of the current ALS, and then what the future one sector would look like. And the big difference is you see there's a lot more magnets for the new ALS. And that gives you more control over the electron beam, and that's why we can make it smaller. Currently, our extraction port for beamline 2.4 and 5.4 is immediately after this third bin magnet in the sector. So instead of having these 3 bin magnets, we're going to have 9. These are the bin magnets. And you can see space is really tight, but there is a little bit of space after this magnet 8 in the sector. And so that's where we're going to extract our light. If we look at this a little bit edge on, we're going to extract the light from 8, but we're actually going to be using big magnet 7 as our source. And so that's what we're doing. The other thing you should note, right, is so we're trying to make the ALSU diffraction limited for soft X-rays. It is already diffraction limited for infrared light. And so the source itself is actually not giving an improvement for infrared itself. And it's making it harder because those chambers are a lot smaller. But we do have an opportunity to redesign the optics that are currently in the storage ring. And so this is again, our first mirror of a current design. This mirror actually absorbs all the X-ray beam while reflecting the infrared light. And so it's aggressively water cooled, but that water cooling is still means that the temperature, so it's absorbing 2 kilowatts of power, which is quite a lot. It's the highest heat load optic in the whole storage ring. And so in some places, there's actually the temperature rises 200 degrees. And what that does is that actually creates a distortion on that mirror. So it's not perfectly flat. And so then when we try to focus our beam down, we actually see some aberrations associated with that. So the new mirror that's going to be part of ALSU is actually going to have a slot in it. And so that slot's going to allow the high power X-ray beam that's happening in the very center go through and then collect the wider angle X-ray light to send out. And with this design, we believe we can keep the temperature to less than 3.5 degrees. And that mirror is going to be a lot flatter, which means we're going to have a much better focus. The other thing we're going to do is we're going to use a newer optical design. This actually I already used the 2.4, but it'll certainly help with the 5.4 beamline. And one of the issues has been, so we have this spin magnet source, and we're collecting all of the light from that source. But if you think of that source as this red trace here, it's extended, so it's almost 1 meter long, and it's curved, right? And so if you take a point from the entrance of it and try to focus it versus a point from the exit of that magnet, they're not necessarily going to focus at the same point. But if you're careful about it, you use a cylindrical mirror to match that orbit radius, you can actually get that light to then focus at the same point with the right angle of incidence and the right curvature of the mirror. So with those two combined, a new first mirror optic, a new focusing scheme, we believe we're going to actually increase the brightness that we currently have at the ALS. So, this is sort of, ray tracing of what a current Beamline 5.4 looks like. And this is what we expect the focus to look like at ALSU. We believe so the flux, as I mentioned, is going to go down a little bit because we're not going to be able to collect quite as much, but brightness we expect to go up, maybe a factor of 5. And we also expect, because ALSU requires much tighter tolerance on the electron beam motion, we expect, a lot of our noise is actually from the electron beam. We're expecting the signal to noise to actually improve a fair bit. So this means we're going to get better sensitivity for all of our measurements. We're going to get faster data acquisition. So one downside, though, is that Beamline 1.4, so we currently have 3 beamlines, but our first beamline that we built is not going to be available after ALSU. And that's because the way the design worked out, it was where the optics were going to block the main pathway to send, get equipment in and out of the storage ring. And so instead of having Beamline 1.4, we're actually going to move that to Beamline 10.4, so a different part of the ring. And so the ALSU project is going to install the first mirror, and then we are in the process of looking for ways to build out the 10.4 beamline for a future IR beamline. But we will definitely have 2.4 and 5.4 starting up when ALSU starts up. Okay, so I'm sort of wrapping up here. I want to mention that we have a long history of collaborative innovation. I talked a little bit about our nanospectroscopy, far IR. We've also done a lot of work with solid liquid interfaces, and that's been with groups here at LBL. So the Samaron groups, Robert Kostecki's group. I mentioned briefly synchrotron photothermal IR. And then we have cryosens. BSISB has been a strong partner with us over time with microfluidics. We also have a project with IR and mass spectrometry. And of course, today, age, AI is always a big thing. So we've been working with them on that as well. And I'd say in general, like ALS in itself is a very collaborative environment. And it's not just me that's done all this. This has been a group of a lot of people. And I do want to thank them. And there's even more people that are on this list. So yeah, so I'll stop there. I'll thank you for your time. And yeah, if you want to use the ALS, come find me. Thanks.
Thank you very much.
Yeah.
Any questions in the room, or if you have questions on Zoom, please type it in the chat or raise your hand.
If anyone has questions on Zoom, feel free to type them in or raise your hand.
Okay, so I do have a question. So you mentioned some of the upgrades that you're doing now with the ALSU versus the ALS.
Right.
Are there any features or anything that you would like to see included but did not pass this round for development yet?
Well, maybe I'll go back to what we pushed for heavily. Let's see, it's the other page. Anyway, so for ALS, maybe this is good enough. The opening angle is the biggest thing that we were pushing for the new ALSU. And really it comes down to the constraint of the chamber. And we actually had a couple options here. So maybe I'll go back. So we have dipole 7 and dipole 8. And we actually had a choice of the extraction point was always going to be after 8 because that's where we had room to stick a mirror in. But we could have taken some light from 8, or we could take the light from 7. And actually that first mirror, part of the dipole of 8 actually is hitting that. And from 8, we can get a larger vertical acceptance, which means we get more light. But because that's so close to the electron beam, it meant that we could only get part of the horizontal amount too. And so we going through the analysis, it looked like even though 7, the chamber is going to cut off some of our vertical acceptance, but we're going to get more light from it because we can accept a larger horizontal acceptance too. And so there's a trade-off there. But if I had to design the ring based on infrared, those opening angles would be a lot bigger. But that's the compromise we have to make it better for the soft X-rays, which is really what's driving the project.
For the SIN spectroscopy, you mentioned the 8-wave number typical resolution.
Sure.
Now in the ALSU, so I don't know actually what's limiting it, but in the ALSU, will that improve to 4 or 2-wave numbers?
Yeah, I mean, so the limit is the signal to noise, really. And so we have interferometers that can scan further. And so like that one example of the phonon polariton, I was scanning at, I did 0.25 spectral resolution. And that's, we can scan the interferometer a longer distance and that's what we get. But the trade-off is the longer you scan, the longer it takes. And then the signal to noise actually goes down because you're incorporating more noise into that signal. And so for a lot of the near field measurements, we find 8-wave numbers a good compromise for getting the spectral resolution you need to identify things, but also getting good signal to noise in a reasonable amount of time. Certainly with ALSU, our dreams come true of a 10 times improvement in brightness. Our signal noise should go up. And so then we can either, do area maps now a lot faster, or we can do higher spectral resolution faster if needed. So it's a trade-off. But it is one of the, we have control over that spectral resolution by doing the interferometry. And that's just, we can set that parameter. And it's different than, you know, a dispersive element where there you might have fixed slits or a fixed grating where then you would have to replace the whole thing to do that. So.
Any other questions?
I was wondering,
Sure.
one quick question. You mentioned your like different detectors you can use.
Yeah.
Are you trying to push also for additional new developments in there?
Sure, yeah. I mean, so this is something, I mean, we've been working on this for, I mean, several years. And so that's, part of it's been a collaboration with NSLS2. So we have several detectors. And so that one of the detectors on that list, or the copper doped germanium detector, was a NSLS2 detector that came here and lived. And then with them, we also developed this helium cooled MCT detector that pushed it further. That one tends to be a good sweet spot for us because it's still very broadband and gets down to low frequencies where there's a lot of phonon modes that we can look at. Going much lower than that, I mean, on one hand, that's where terahertz time-based systems can start to come up to that energy levels. And so the synchrotron is starting to have less of an advantage. And it's also where the ALS source itself is starting to die too. So, but down to about 100 wave numbers would be good. And so if we can get a detector, and certainly if we could get one that's not requiring liquid helium all the time, that would be great too. So.
No further questions. Thank you again.
Yeah.